Okay.
Does what means consciousness also involves from qubits? Also, what about symmetry aspects of monads qubits? You prefer to talk, rather?
Oh, yes, sir. Thank you.
Okay.
I have a curiosity in my mind. Just for curiosity's sake, I was asking this question. Does the entire things you have discussed, I am connecting that with the consciousness, the biggest problem, still the biggest problem. Does the consciousness ultimately evolve from qubits, like the quantum? Our brain is behaving like a quantum computer, as said by the Hameroff and Professor Roger Penrose theory. It is coming out from the microtubules inside the neurons. I am just curious how the consciousness evolves. What is this? Is it just qubits? And my second question, or just curiosity, is I just want to know what are the symmetry aspects of these structures called monads or qubits? Do they have any anti or the counterparts also, just like everything in the universe is based upon symmetry principles?
I missed the verb of the second question. What do you say?
As all the laws of nature, they are built on symmetry property. There is
the symmetry property?
Yeah, symmetry. So just we are talking just like here monads or qubits. So are there any counterparts like anti-monads or anti-qubits, just like the universe running in the backward direction? Did it signify that thing, or I am not able to interpret that thing? Thank you.
Well, thank you. A basic assumption in the Leibniz perspective is the fact that basically his view is not, if we compare Leibniz with the Cartesian view, in which we have a separation between res extensa and res cogitans, and that means between mathematical and physical world, we might say. In Leibniz, we have this kind of organicistic view in which actually even the monad, even the infinitesimal part of the universe as a soul, or as an infinitesimal automata, in the sense that in the Leibniz universe, there is no separation between nature and mind. I mean, nature, it's physical and mental. This, perhaps I didn't stress this aspect, but I was trying to distinguish physical world and natural world, in the sense that usually when we talk about physics, we think about the interaction of matter and light, but of course the soul and the mind, it's put apart. And in Leibniz perspective, there is this connection between the two aspects. And in this sense, the wave function plays a kind of role of soul, I must say. But in any case, the whole, I mean, the core of the argument, also according to Wheeler's perspective, is the fact that just like the phenomenon, the quantum phenomenon, appears when it provides an answer to a yes-no question, and what is going in between remain out of our knowledge, is there, it's real, exists, but remains out of our knowledge until it gave an answer to a yes-no question. In this sense, there is also a connection between a physical approach and the logical approach, and also how this is connected with the description of nature itself. And in this sense, when the concept of the universal computer came out, Leibniz was thinking of a universal computer somehow like Deutsch or like the universal computer was, can say, an overlap between mental and physical, because for Leibniz, the monadology is the structure of the universe. And then when we talk about Turing machines, we have the logical concept, that is the calculus ratiocinato, that of course Leibniz was very conscious and were aware of that. But also Leibniz wanted to somehow to relate the calculus ratiocinato with the system of nature. And of course, all Leibniz discussion is in the metaphysical realm. But the point is how we can project that kind of view in modern terms. And this was the point of view, what Wheeler was doing in his article. And I found this very actually, for me, it was interesting that when I read Leibniz, I didn't know about Wheeler. And reading Leibniz, I said, oh, but it seems that he's talking about qubit. You're talking about quantum information. And then when I read of Wheeler, I said, well, perhaps there was something that was not just, there is a kind of resonance that actually Leibniz perspective is in that way. But also, it seems to me important, the difference between the two projects of Leibniz. One is the calculus ratiocinato. That means it's all the reflection about the mechanical procedure. But the other is the universal characteristic. And the difficulty of the universal characteristic was the character of symbols. These symbols for Leibniz has to be something like ideogram. And actually here there is also a connection with Leibniz and the Chinese thought, because he thought somehow that in the I keying there was a key, because that was a binary system that could be a key to understand the ideogram. And then that ideogram or the kanji were a sort of the symbol that Leibniz was looking for, his alphabet of thought. So this is, I mean, two aspects. And it seems to me, fascinating that perhaps in the concept of the universal quantum computer, the two projects come together. Cioè, the physical machine and the natural machine coalesce in the universal quantum computer. But perhaps I didn't answer to your question about consciousness. Actually, I didn't answer to your question because I don't know. I have no answer because I didn't go deeper in that kind of
I really thank you, and I also thank all the organizers also because it is my first summer school or conference or workshop attendance here. I am from physics field mainly, but I was very anxious to attend a philosophical conference, and I think I am gaining a lot in this summer school. Thank you very much.
Thank you.
There is another question by Thibault Pochon.
Okay, hi, do you hear me?
Yes, sir.
Okay, thank you very much for your lecture. I just want, I didn't really get why you claim that there's no natural bits in nature, only qubits. I didn't really understand that part.
Well, because qubits is the real stuff, in a sense. So qubits is what is in nature, what is there, what exists. Bit is the answer to a question. A bit is the answer that we get when we try to extract information from the qubit. In this sense, okay. A qubit is the quantum, I mean, is the physical system. And the quantum phenomenon, as Wheeler called the answer to the yes-no question, is a bit. Because actually, when we pose a question, when we arrange an experiment in order to have an answer, or we project a computation, a quantum computation, okay, qubits are the real stuff. But the information that we get are bits. In this sense, I would say that qubits are real and bits are abstract, because bits are the symbols that we use in the language of our knowledge, because knowledge is a symbolic universe, and this symbolic universe is made of bits, not of qubits. In this sense, this was what I wanted to say. Of course, we can also reverse.
I see.
The point of view.
Well, there are 2 questions by Vincenzo Pano.
Okay, thank you.
Vincenzo?
Okay. Can you hear
We are
me?
not
Yes.
listening
Okay.
you. Okay.
Thank you very much, Rossella, for your wonderful presentation, very rich, both from a philosophical and a historical point of view. I have two observations. One about this statement by David Deutsch that quantum computers can do something that Turing machine cannot do, even in principle. This statement is very strong. It is clear that from a complexity point of view, we know that quantum computer can do something that indeed Turing machine cannot. But I would like to know your opinion about the possibilities that quantum computer are not Turing machine in a more deep sense. A second one is that there is something that from a very, very, very speculative point of view, but your presentation was very speculative. So I feel myself, I feel myself
encouraged to
encouraged, yes, to be very. When Wheeler and above all Deutsch says that reality is made of qubits, there is something that, to my feeling, is not in the right direction, because to understand the reality, it is clear that we have to propose a model in which matter and mind coexist. This is clear, and the sense of David Deutsch and Wheeler perspective is exactly in this direction. To understand the nature as made both of mind and matter. But the feeling is that when we speak about mind, there is something intrinsically non-linear from a mathematical point of view. It is something which it is not possible to distinguish between cause and effect, because the effect became the cause of the cause, and this is clear in nonlinear equation, like equation of general relativity, that from this point of view are very clear. That is, you cannot say that matter cause the structure of space-time, because at the same time space-time cause the distribution of matter. So you have two things that cannot be distinguished from this point of view. On the contrary, quantum mechanics, above all in the interpretation proposed by many words, is strongly linear. Is very strongly linear. My feeling is that notion like entanglement, that is non-linear, that is from this point of view is something made possible by quantum mechanics, could be something more fundamental, like for instance in Maldacena and Susskind hypothesis that ER, EPR are strictly connected. So EPR, that is Bell correlation, became something nonlinear, that is something connected with wormholes, that is a solution of Einstein equation. All this is very speculative, but okay. Thank you again for your conference.
Well, as for your first observation, that in principle, tasks that in principle are not possible classically, as I said, it's not the Church Turing thesis that's been put into discussion, but it's the kind of process that is different. In fact, not the result. Any result that you can get with a quantum computer in a reasonable amount of time, well, reasonable, it's difficult to define, but can be obtained also with the just think of the factorization, for instance. No, the point is that, but then also, what does? Yeah, I agree. In principle, is a very strong claim, because in what does it mean, in principle? I mean, if we consider that the descriptions in terms of complex numbers, we can say, okay, it's possible, because then you are using complex numbers, and in the classical way, you don't use complex numbers. It's not that in principle, it's not possible. I mean, just apply the same structure and you get the same results. But it seems to me that the point is to highlight that there is something like the quantum interference that has an effect also in our understanding of the notion of computation. And actually, I think that I've stressed that the Turing's limits remain, because the distinguishability limits that are posed by Turing are not in discussion. Okay. And there is the first point of contact between physics and logic. Now, the point that, okay, what makes a function calculable is the fact that the finite means that are justified by Turing with the well-known argument. But then, when you consider the process, when you consider the agent that is a physical system, at that point, you can consider also that the procedure can be different. At that point, of course, you compare the result, but not the procedure. And this, well, as for the qubit, and I think that the position of, perhaps I was not clear, but it seems to me that the position of Wheeler and Deutsch are not the same, in the sense that somehow Deutsch is more realistic than Wheeler, because Wheeler is concerned about the emergence of meaning, let's say, and so is concerned about the phenomenon. And he wouldn't say that qubits are real. It's Deutsch that is more concerned with the reality, and said that the reality actually is the qubit, and the nature is made of qubits. But again, it depends if you put the accent of the ontological aspect or on the construction of meaning.
Thank you.
Thank you.
There is a question by Clarissa Lee. Are you connected?
Yeah. Hi. Thank you very much for this very interesting talk. This is actually a question that tries to connect what you were saying about Leibniz. You were saying something about his, or maybe I misunderstood it, his universal wave function or wave matter, right? And you were talking about it in relation to interference. So I'm just wondering whether you see Leibniz's conception of wave. I know there's actually a mention of that in his monadology, even though it's been some years since I've read Leibniz. Whether it's a sort of a precursor to thinking about quantum interference, since you were showing the example of the mirrors and in the STM. And I'm also thinking how that actually also connects to what you were saying about Wheeler as well, and his idea of maybe I got this wrong, information as being emergent or being of kind of being in an emergent form. But anyway, now I can't ignore my relation, my connection to Wheeler. But I'm just curious about what you were saying about Leibniz and whether he could, like, if you follow his trend of thought, whether we can use that to, you know, chart the genealogy for thinking about quantum interference, and then therefore connect that to our own understanding of quantum information.
Thank you. No, well, As to quantum interference, actually, this is a good point, but I wouldn't say that there is the same kind of it's more correlations that there are in the Leibniz picture, in the sense that, okay, I use the term universal wave function, but perhaps I was in quotation marks, in the sense that I was applying the Everest terms of the universal wave function for describing the monadology. But in the monadology, of course, the fact is that each monad this is interesting. There is a unity of it's not perceivable, no, it's not visible, no, it's a simple substance, and it's a unit of perceptions. Now, this perception play a very subtle role, because this perception are described as the inner continuity principle, and also like a kind of correlation function that allow us monads to let's say, to see each other, because each monad acts as a living mirror of the universe, and like a mirror does not communicate but just reflects.
Mm-hmm. Yeah.
And so it's interesting, because there is this unitary transformation inside the monad that is the perception itself. Mm-hmm. But then, of course, Leibniz didn't give any kind of explanation of how to come out from the monad. Actually, Kant wrote a physical monadology just in order to face this problem, and because he was trying to conciliate the metaphysical approach of Leibniz with the physical approach of Newton. And this is a very interesting reading, because the way in which Kant considered the possibility of applying the universal gravity of Newton to the monads of Leibniz. And in a sense, this is the same kind of problem that was facing Wheeler when he was trying to use the description given by Everett for the quantum gravity, in order to because the universal wave function was something that could help understand and to find a connection between the two.
Okay, thank you.
Thank you.
Well, there is a final question by Enrico Maresca.
Yes.
Yes, I'll try to be as quick as possible. Okay, can you see? Yeah. So I was wondering about the implications of this multiversal interpretation of the computational process with reference to Wheeler and Deutsch in particular. Because as I see it, in Deutsch's principle, computation is basically an emergent phenomenon, so to say, from the interaction of different qubits, so multiversal entities. But in a situation like the delayed choice experiment, one of the implications which Wheeler suggests is that we allow backward causation in quantum mechanics. But if the computational network, for example, the computational process itself is an emergent entity through the interaction of qubits, then would this mean that we also might allow backward causation or an inversion of the time order into computational situations, into quantum computation? Because in computation, we have a sequence of steps, so to say, which are ordered in a certain direction from the beginning of the computation to the outcome. Would this allow some kind of also reverse approach, so to say, from a temporal point of view?
Well, of course, you can use that suggestion and to develop that suggestion. But what Wheeler wanted to point with that example was the fact that whatever happened between the two semi-transparent mirrors is something that remains a mystery. And information, just what quantum physics said is that you get information, you get knowledge only when you interact with the system. That means only when you perform a measurement. That means when the photon reach a detector. In the meantime, yeah, you don't know what is going on. And the fact that you can decide to pose the second semi-transparent mirror at the very last moment show somehow the paradoxical situation that is there. But also, yes, from a sense, a paradoxical situation. From another, the fact that quantum theory suggests that physical knowledge is what results from interaction, that any physical property is a relational property. It's not something that is there, but is something that results from the interaction. As any of us could be, I always say, a killer of a saint, depending upon the people that met in his life. The same things happen for the quantum system. No? What we get in our knowledge is the result of measure, and this was the reason of the quantum, the yes-no elementary quantum phenomenon. And I stress phenomenon, not noumenon. The noumenon is inside the Mach-Zehnder interferometer. But of course, this can also, yes, can also suggest that there is a retraction. You can go back and exploit the fact. Yes, sure. Thank you.
Okay, thank you for the answer.
Thank you to everybody. We can close the session. I should like only to stress a question to Rossella, because she probably knows it. And this concerns the fact that the Wheeler standard delay choice experiment change not an event, but simply a possibility of event.
Yeah, sure.
Together with Gennaro Auletta, we have an improved version of this experiment with two device of detection, one on a long path, the other on the short path. You have registered event that is registered of interference or registered of the path that can be changed by acting on the last, not the second, because we have a lot of semi-reflecting, of mirror beam splitter and so on. And so you change an event. So there is, in some sense, the possibility of a retroaction. The other one concern is a very interesting point of the shadow photon of Deutsch that recall Einstein, Gespensterfeld, both fields of Einstein, virtual waves of Bork-Hammers-Later, Lone Pilote de Broglie.
Yeah, sure.
Franco Sellery and our empty waves. The last possibility in this field concerns some work with Alexander Affert, where we assume that in one of the two paths we have no photon, that is, no thing. And this detection can change the physical situation. It's similar to your proposal, even if probably it is a different metaphysical background. So thank you very much to everybody, and
thank you.
We hope for this wonderful reconstruction, very focused on metaphysical, the reopening of metaphysical questions, the fact that quantum theory is in the history of science, there is no theory, most quantum mechanics, that open metaphysical questions that are considered devoid of meaning. In particular, Leibniz monadology has been a case, but also Cartesian philosophy and a lot of questions. This is very stimulating, not only philosophy of science, but philosophy in general, I think. The importance to study foundations of quantum mechanics is relevant, not simply for philosophy of science, but for theoretical philosophy, where the disputes are not connected to questions concerning the foundations of science.